This lesson logic gates, logic circuits. Lesson objectives. Use logic gates to understand principles of logic. Draw a logic circuit for real-life examples using logic gates. Definition. A large number of electronic circuits in computers, in control units and so on are made up of logic gates. These process signals which represent true or false. What does mean signals? Signals can be represented as on or off, 1 or 0 as well. The most common symbols used to represent logic gates are shown below. Not, and, or, not, nor, and XOR or exclusive OR. Mil symbols or military symbols. Not gate, OR gate, AND gate, NAND gate, NOR gate, and XOR gate. There are many different logic gates, but we will concentrate on this. Truth tables. Truth tables are used to show logic gate functions. Description of the 6 logic gates. NOT gate. We have one input and one output. The output X is true, 1 or 1, if input A is not true or is off. Truth tables for X equal not A. Two inputs 0 and 1, output will be 1 or 0. NOT gate examples. Temperature detector above 20 degrees on or off, central heating on or off. AND gate. 2 inputs A and B, 1 output X. The output X is true, 1 or on, if input A and input B are both true. Truth table for X equal A and B. AND gate example. Person, sensor and alarm switch, burgle alarm. if both the person sensor and the alarm switch are on, the burglar alarm is activated. OR gate. Two inputs A and B, output X. The output X is true, 1 or on if input A or input B is true. Truth table for X equal A and or B. We have two inputs A and B. Input A 0, 0, 1, 1, for input B 0, 1, 0, 1. Output X 0, 1, 1, 1. OR gate example. Front doorbell switch or back doorbell switch, doorbell on. If either the front doorbell switch or the back doorbell switch is pressed, then the doorbell rings. NAND gate. The output X is true, 1 or on if input A and input B are both not both true. The output X is true, input A and input B are not both true. Truth table for X equal not A and B. Input A means 0, 0, 1, 1. Input B 0, 1, 0, 1. Output X are 1, 1, 1, 0. NOR gate. The output X is true if input A or input B are not both true. Truth table for X equal not A or B. Two inputs and four combinations. Input A 0, 0, 1, 1, input B 0, 1, 0, 1. Output X 1, 0, 0, 0. XOR gate. Four combinations. 0, 0, 1, 1, input B 0, 1, 0, 1, output X 0, 1, 1, 0.
Coming home from school. Gonna jump in the pool. Bam, bam, bam. Oh, hey. Can I? No. Moby. An android? What's with that guy? Dear Tim and Moby, why does my phone get hot when I have a lot of apps running? From Sylvie. Hey Sylvie. If you've ever opened up an electronic device, you probably saw one of these. This is a circuit board. It holds the main parts of a circuit and controls the flow of electricity to them. Close up, you'll see something like little pathways. In fact, that's just what they are, paths for electricity to flow from one piece to another. Right, as electricity streams through the circuit, it's also passing along tiny pieces of information. The current is actually pulsing in a kind of code called binary. Yep, binary is usually represented as ones and zeros. These values are known as bits, but they don't have to be numbers. You can make a binary code out of any unmatched pair. Braille is a special kind of binary where the bits are raised dots and blank spaces. In Morse code, the bits are long and short pulses of sound or light. And in digital circuits, the bits are low voltage and a higher voltage. In other words, computers and other electronic devices think in a binary code made of electricity. To process the code, they rely on something called a logic gate. A logic gate is sort of like an electric switch.
Okay, so with the first example, we have headlight warning system on a car. So this is the sensor here for the light sensor. So I'm a visual learner, so what I'd like to do, I'm going to draw the picture here. So I have the sun. If it's sunny, then it's going to be 1. If it's nighttime, there's the moon, then it's going to equal 0. Then I have the headlight then, so that's the person actually turning the headlight on and off on the car. So here's the headlights, that's the bulb, and it's on, that's going to equal 1. And then the bulb with the headlight, there we are, there's going to be 0. So if you look at the actual gate itself, that is the NOT gate, NOT. And then here I have exclusive OR, XOR. And then the headlight warning light will be here. So I've been given the circuit, so now I will do a truth table. So here's my truth table, and Q is my output. So this will be A at this point here. This is going to be not A, and this is going to be B. And the output here is Q. So I'll put some values for A. Not A, so there's going to be the inverse or invert 1, and this is for B, so B can either be 0, 1, 0, 1. So when it comes to actually calculating Q, then XOR, so exclusive OR, so you only get an output when these two are different, so high, low, or low, high. So I have 0, 0, so output will be 0. 1, 1, that will end up being 0, 1, 0, 1, 0, 1, 1. So these are the only 2 times this headlight will actually work. So if I were to look at this then, so for A, so if it is the light sensor is on, that means it's sunny, so that means that we don't need, it's sunny, so therefore there's no need to turn the lights on, unless of course in B the person decides to turn the light on. So that is, so it's here it's actually dark, so we need to have the light. Here it's light, but the person decided to turn it on to get the output. And then on this one here, which might cause a few problems or questions, here it is, the light has been turned on, so someone's pressed the button, and also the light sensor is actually being turned on as well, so it's cancelled each other out. So that one there looks a bit strange, but the logic is that it's cancelled each other out. But in that case, you're not going to turn the light on and also have the light sensor, so this is going to override itself. Okay, that is exercise 1. And then to represent it in Boolean logic, so we're going to say not, so that is the not sign there. It's not A, because A has been inverted, and you do XOR, and then you have B as the, so, or another way to represent it will be like that for the Boolean equation. Exercise 1. Here we have a car safety system where we have the driver's seatbelt. So with the driver, if the seatbelt has been locked, then you will have a high signal. If it's unlocked, you get a low signal. And here we have the car doors, that the car doors, if it's closed, we have a high signal. If it's open, then we're going to get a low signal or no signal. So this is the light will appear if either the seatbelt hasn't been locked or the doors are open, then the light will come on. And if there's no seatbelt and the doors are open, then the light will come on. So I'm a visual learner, so I'm going to say locked, and I'm going to say it's going to be a 1. Unlocked, it will be at 0, and then the same with the doors. Closed, 0. Open will be 1. That's just to help me to reinforce. And if you look at the actual circuit, you have AND gates here, and you have a NOT gate. So I will now do the truth table. We have A, B. I'll label these as A, B, C, D, and E. I'm now going to have, I will also, to make it easier for myself, the output for B and C, I'm going to call that F here. The output for D and E, I'm going to call it G. And then the output of F and G, I will call H. And then the output at this point here of H and A, going into that AND gate, will call that J, and then you have Q then here as being the final output. So I'll put a combination 0, 1, 0, 1, 0, then 0, 1, 0, 1, 0. I've repeated myself there, I just realized. Okay, so let's look at A. So A, I will deal with A later. So B and C go into a AND gate and the output is F. So B and C, so with an AND gate, you only get an output when you have high and high. So 0, 0, 0, and 1. Okay. Same with G, with D and E, you only get an output high if it's high and high here. So G, it is going to be, so looking at D and E, we have 0, then 0, 0, and then high and high will give you output high. So now F and G, and you get the output H, so it's another AND gate. So with the AND gate here, F and G, 0, 0, 0, and only when it's high do you get an output high. So J, looking at J now, what you have, you're bringing in the first circuit A. So A is another AND gate, so we've got A and H. A and H will be the output for J, so that's going to be 0, 0, 0, and then you have 1 and 1 will be 1 there. Now they lead into a NOT gate and the output for Q. So with the NOT gate, which is going to be on J, got 1 input and 1 output. So it's going to invert. So 1, that means the light will be on. 1, the light is on, the light is on, and the light will be off. So the only time the light will be off will be on this point here, and that is when you have, come back to here, you have the door locked and the doors are closed. So only at that point where the seatbelt is locked, and the I have these the wrong way round. So there we are. You have the seatbelt here. You have the seatbelt locked, and you have the doors closed. So these are the doors. That's the seatbelt. So only when it that complies, that works, that you get no output. So the light will always come on if one door or two doors are open, or the seatbelt is locked. Seatbelt hasn't locked. To represent it in a Boolean logic, as a formula, so we have not, which is that part there. It's going to be A and, so not A and, open bracket, B and C, and D and E. Now I've used brackets just to bring these together, so it is B and C, D and E, and is for the AND gate here. So they're joined together, they're combined here. And we have and A, and all of it then is turned into a not, where it's all inverted at that point there. So if I were to represent it differently as a formula, it would be A and B and C, bracket, and D and E, bracket, and then I can put the line across, which will be the not for all of it. And that is the car safety system completed. Thank you. So, okay, yes.
We should analyze V more than 1000 liters. This is a binary values equal 1. It does mean V. Next, S less or equal 15 meters second. This is a 0. Binary values equal 0, not S. Next, T less or equal 750 degrees. This is our 0. Not T. T not. And last one, S more than 15 meters seconds. This is our T. S binary value equal 1. The output S. And we should write logic gates between these inputs. First we AND gate between V and not S dot. Second, about temperature and speed, we used AND gates. With two logic expressions between, we use OR gates, or temperature. And our final expression has x equal V dot not S or not t dot s. For this expression, now I will create a truth table. For input v, we have three inputs. For three inputs, we have 8 combinations. 0, 0, 0, 0, 1, 1, 1, 1. For input t, 0, 0, 1, 1, 0, 0, 1, 1. For input s, 0, 1, 0, 1, 0, 1, 0, 1. Next logic expression, we have not s. Not s, it does mean opposite of for s. 0, not s, 1, 0, 1, 0, 1, 0, 1, 0. Next formulas v dot not s. Так, for 0 and 1 output 0. 0 and 0, 0. 0 and 1, 0. 0 and 0, 0. 1 and 1, 1. 1 and 0, output 0. 1 and 1, output 1. 1 and 0, output 0. Next, not t. Opposite t. 1, 1, 0, 0, 1, 1, 0, 0. Not t dot s. 0 and 1 output 0, 1 and 1, 1, 0 and 0, 0, 1 and 0, 0, 0 and 1, 0, and 1 and 1, 1, 0 and 0, 0, and 1 and 0, 0. Last, we should use for OR gates for two logic formulas. V dot not s or not t dot s. 0 or 0, 0, 0 or 1, 1, 0 or 0, 0, 0 or 0, 0, 1 or 0 output 1, 0 or 1 output 1, 0 or 0 output 1, and 0 or 0 output 0. This is our last logic expressions. Here truth table for these logic expressions. For decision this task by computer, I used logically demo version site. We have input controls, output controls, and here logic gates. First of all, we have three logic inputs, T, S, and V. I take a toggle switch for this logic inputs. First input, this is a T. Second input, this is a for S. And third input, this is a for V. T, S, V inputs. Now, first of all, I should create a not T. For not T, I use not gate, logic gates, and I will combine two logic inputs. Next, for formula, V dot not S. Next, I will again create a node S. And for first formula v dot node S, I use AND gate. Here. Next, node T dot S. Here is node T, this is S. We should again use node AND gate. Between AND gate, we use OR gate. I take from logic gates OR and combine two logic inputs. Now I have an output. For output, I use a light bulb. And I switched on with a light bulb. First, from truth table, we have, if we have 3 input 0, output 0. If input V and input T 0 S1, output is 1. If V and S0 T1, output equal 1. This is our logic gates by computer. И 6 опор. После того, как установлен предупреждающий сигнал, если какие-либо из дверей или окон открываются, сигнал тревоги будет звучать. Используется вентиль OR или логический элемент. Или таймер позволяет владельцу дома, чтобы войти в дом с передней или задней двери и отключить систему сигнализации перед тем, как зазвучит сигнал тревоги. На каждую входную данную можно дать значение 0. Ложь, низкий или выключен. Это означает, что они не обнаружили злоумышленника. В результате сигнал тревоги не будет звучать.
Там 3 или так? Смотрите, 2 двери и 6 окон. Слушай, они сама парируют, Так, 6 входных данных это у нас окна, 2 входных данных передняя, задняя дверь. Изначально у нас входные данные равны 0, 0. Какой элемент используется логически? Или OR gate.
Как вы видите, у нас тут 6 входных данных. Это сначала окна и еще 2 входных данных, это передняя и задняя дверь. То есть мы еще используем логический элемент или, как вы видите, и также после входного данного, где дверь, у нас есть таймер, так как когда заходит владелец, он, когда заходит, сразу выключает таймер. И дальше у нас в конце идет еще раз прибавление логических элементов. И если везде наши входные данные 0, то сигнализация не работает, не сработает. Вот.
А если какая-нибудь из них дверь открылась?
А если окно или дверь откроется, то сразу же будет сигнализация и будет сигнал.
При выходе будет выход будет output у нас 1,
Да,
дальше
да, и
естественно,
сразу-
сигнализация заработает.
Да, так как у нас логические элементы или сразу.
Хорошо, спасибо.
Question I'm going to ask, let's think about this first, okay, is that why do we use logic gates? What's the relation between logic gates and practical life? So what kind of answers will you come up with? Why do we use logic gates?
Why?
Yes, why do we use logic gates?
When we switch off or switch on the light.
The lights, you're thinking lights in general, okay. But what about, say, can we link that with a computer? What's the link between logic gates and a computer system?
Yes, CPU.
CPU. So the important part is, in a CPU, you have millions of logic gates inside the CPU, and they're making decisions for us. So if you want to do addition, if you want to do subtraction, multiplication, branching, division, yes. So all of that is down to do with the logic gates. So logic gates going to make decisions for us. So that's the link between logic gates and the processor. Okay, so the processor is full of logic gates. So you mentioned lights as a practical activity, as a practical process. So okay, can't put my words. Filming. The camera when it's filming, I start panicking. Okay, so do you understand logic gates? How would you regard your understanding of logic gates?
I understand that logic gates is an important part of CPU that helps us to make different decisions and problems.
Okay. So, in an exam situation, how would we test your knowledge on logic gates? What kind of questions would we be asking on logic gates?
To complete the truth table and maybe to draw the circuit by using this. Maybe we will be given for table and circuit, and we must write the formula.
Okay, thank you. And why do we have the symbols? You know, we use symbols. Why are the symbols always got to be a set symbol? Why can't we use different symbols?
We can use it if we write it in the beginning, like triangles and words like that.
Okay. Why do we simplify Boolean equations?
To save time.
Save time, so the calculations will be performed faster. And also you're using less what we call transistors in the circuit. And that's why the circuits are smaller. And the processor gets smaller and smaller, and you get more in that case. Okay. Did you enjoy the topic?
This topic gives for everyone the most important meaning of CPU, and this lessons was understandable and interesting for everyone, I think.
Oh, did you find it interesting?
Yes, all of these logic gates have something interesting.
And I like draw.
You like the circuit? Okay. So, is this used in other subjects, like in physics or chemistry?
In physics, yes.
Oh, okay. So they're linked between this subject and physics.
Yes.
Okay. Thank you.